First of all, you can hear me in the back? Yes? Okay. I apologize. I think the original date of this talk was a couple of weeks ago. There was a personal event, so I had to delay it for a couple of weeks. I'm very glad to be here, and I enjoy the little historical presentation of the mathematicians. What was surprising and fresh for me is that in computer science, when we go back 70 years, we call it classical research. But I was surprised to hear that somebody in the 1870s is called a modern mathematician. So that gives you the different perspective that I now have going from the mathematics major to a computer science major. Another thing that I wanted to forewarn you of is that even though, or maybe because this is a mathematical colloquium or mathematics department colloquium, I deliberately removed all mathematical formulae from my slides because I don't want to be questioned. If I get questions, then I will be very confused. So now I will begin my talk. But if you have questions about the underlying math, there is a lot of, I wouldn't say math, but statistics behind everything that I will talk about today, which means that you are in a very good position to suggest collaborative research, because as I said, I am not a very good mathematician, but you are. All right, so topping modeling, as Professor Kang sort of introduced, is my major topic. Topping modeling is a branch of research within machine learning based on statistics, and the purpose of topping modeling is to discover underlying thematic patterns in textual data, okay, from unstructured data, including text. It has been most widely used for text modeling, but it can also be used for analyzing and understanding audio data, image data, multimedia, scientific data, and so on. Okay. So the topping model that I'm going to focus on is called the latent Dirichlet allocation, and that was first proposed in 2003, and in the last decade or so, it has been heavily researched. There's a lot of research papers on topping modeling, and the reason for that is that it's such a versatile model that can be used in all kinds of unstructured data to help us understand what are the patterns, what are the recurring patterns and themes in that data set, okay? Which is sort of, I mean, if you think of machine learning, you may think AlphaGo or the Jeopardy playing machine, but actually a lot of machine learning is for discovering, uncovering, understanding patterns in data, right? So let me illustrate with an example what a topping model is and how it works, or what the input and output of a topping model algorithm would be. So let's imagine we have a corpus. Okay, a corpus is a data set of text documents. So we have a corpus of the articles from the New York Times. Okay, and one of the articles is about the recent lawsuit about this venture startup company called Theranos. They were making these kits to test to conduct blood testing. But anyway, there was a lawsuit about some kind of what do you call it? A fraud, okay, in how they were conducting the research. So when we read a paper like this, this is sort of like the English test, right? So if you've ever taken the TOEFL or something, they give you a passage and then you have to answer some questions about the passage. It's sort of that the purpose you can think of topic modeling is to automatically answer these reading comprehension tests, such that, okay, when we read this article, we can understand that this article has several themes, one of which is biology, another is about startup companies, and another is about legal issues, law. Okay, and we know this even, okay, we would like to, as humans, we know this even without somebody telling us beforehand that this article is going to be about these three topics. Okay, so the purpose then is for the machine, the computer, to automatically discover that this article is about these three topics and some other minor topics as well. And in addition to that, each of these topics is represented by some probability distribution over the words in your vocabulary. So I'm representing each topic with a set of words that have the highest probabilities in that topic. But in fact, we actually, for each topic, the dimensionality is the same. It's over the entire vocabulary in your data, but they all have different probability within that topic. So what that means is, in this law topic, these are the words: accused, lawsuit, legal, reported, regulatory. These are some of the words with the highest probability of occurring in that topic. Okay, and what you should know is that what the probability distribution is for each of these topics and what these topics are, that is all not given to you before anything. Nothing is really given to you except this corpus of text documents. Okay, so then the output, okay, so this is what happens. You feed to this topic model algorithm a bunch of articles from the New York Times without any predetermined knowledge about topics or words or anything like that. So there's no notion of dictionary and law and regulatory. These words are related in any way. We don't have that knowledge beforehand, but after running the model, it's going to be able to, the results of the model are going to be able to explain each document in terms of topics, which topics are prominent in this article, and explain the topics in terms of the words, which words in my vocabulary are highly likely to occur for each of the topics. Okay, so that's the main purpose and of this topic model. And a graphical view. So if some of you may be familiar with graphical models, some of you may not. But this is what actually happens. Observation. So in a graphical model, you have some variables of the model that are observed. That means we can see. That's the input that we get. Okay, so into this topic model algorithm, we feed these observations. And these observations are in terms of the document. So I have document number 1 that contains these words. I have document number 2 that contains these words, and so on. Okay, so these are the observed variables, observations of my data. And then from that, we discover these topics, and we discover the distributions of the topics for each of the documents in my data. Okay, so what that means is, for example, so we have these 3 topics, green, represented by these colors, green, orange, and purple. And you can kind of see, and I made this up, but the green topic is about biology, the orange topic is about this startup thing, and the purple topic is about legal issues, right? So then what that means is this first document that's represented by that bar with a lot of orange is mostly about this, there's some article in the New York Times that's mostly about technological startups, but then there's maybe a little bit about biology in that article, and then maybe a little bit, a very, very little bit about legal issues. But the article that we were looking at before about the company that was sued is perhaps this this last third document where a lot of it is about biology and the venture company that's about biology, and then there's also a pretty large portion of the document that's about legal issues and lawsuits. Okay, so and the way it's done is that for each word in my observation, let's say this is the article that is the third bar right there, we assign, or the model tries to infer. The model tries to say, which topic did this word company come from? Which topic does this word lawsuit come from? Okay, so this is sort of a generative view of how do you generate each word in this document. So if I'm a writer, okay, so this is sort of a different perspective of how this model works. I'm a writer. I'm a journalist for the New York Times, and I want to write an article about biology, this biology technology biotech company, how it's legally accused of fraud. Then I first want to write the first word. Okay, so I say, well, I'm going to write this first word about biology, and so I look in my biology topic, and my probability distribution tells me I should choose medical. Okay, then I write the word medical. The next word I'm going to the next word I'm going to write about the legal topic. Okay, and so I look in my legal topic, multinomial distribution, and the distribution tells me I should write the word lawsuit. Okay, so I write that. So what that means is, if you're given not just one document, but a bunch of documents, let's say 1 million documents, some words are going to occur together many times. Then we can say, aha, there's a topic. Okay, and this topic is composed of these words that frequently occur together. Okay, and also we have these sets of documents with certain topics that co-occur many times together. Okay, so let's say technology and mobile device. Okay, so then we can have some kind of a distribution of topics for each document. Okay, so a lot of it. So it's all this sort of repeated inference over what's the best topic for my word. What are the best topics for this article given these topical distributions? And sort of you just iterate through all these guesses that you're making. Okay? And then the outcome of the model, then after it converges, okay, after it converges to some kind of a distribution over the topics and distribution over the words and distribution over the topics, the outcome of your model at the end of convergence looks like topics and topic distributions of the articles. Okay, so this is the basic topic model, and I hope I explained it well. There are problems in this basic topic model, and this model is called the latent Dirichlet allocation. There are actually many problems with this basic model of basic topic model, but we identified 2 problems that we wanted to improve upon. And to be fair, I mean, there have been many thousands of papers that deal with problems of this basic topic model, and they do all kinds of things like, why don't you model authorship in addition to topics? Why don't you model citation networks? All kinds of different things. But the 2 problems that we wanted to address are actually very inherent and intrinsic assumptions in this basic topic model. Okay, so the first assumption is this assumption of exchangeability. So here we're assuming that the word, let's say the word defendant here, okay, there's the word defendant. It has the same meaning and same distribution, basically, anywhere that the word occurs. Does not care. It's very agnostic about the context. Okay, as, which is the previous word, does not contribute anything to how we find the topic for this word defendant. For every word in the corpus, we don't care what the local context of that word is. Okay, which is not a good assumption, but it's a very simplifying assumption, and as you can imagine, the statistics become very simple when you make that exchangeability assumption. So Jun Kim, he's my graduate student, and I don't know about the math department, but in computer science, all of the research is done by graduate students, and I just present the research. But I discussed with him. So we've been discussing, Jun and I have been discussing this notion of local context for several years, that, this assumption of a word does not change its meaning wherever its document appears and what words that it's next to, that just does not make sense. So we wanted to see if we can also capture the local context within a certain small window around each word. Okay, so he came up with this size, magic number 7. That's I think it's because in psychology we have the brain capacity to look at 7 things at a time. Which experimentally seemed to work very well for us as well. So basically, we have this narrow window. Okay, so we're looking at each word not only by itself, but with this narrow window. What it's showing right now is actually more than 7, but you can sort of imagine if the window is of size 7. Okay, and so by looking at this, and this is why the model is called dual context topic model, which is slightly different from what the poster said, but we keep track of 2 different contexts for each word. So before, in the basic topic model, we only keep track of the document context of each word. We know that this word law, okay, occurred in this document, let's say 5 times, and then in document 337, 1 time, and so on. So we have the document context for each word, but now we're proposing to revise the model such that we're also keeping the local context of each word. Okay? So the second problem that we thought was very silly of this LDA model is that this model thinks of words as just each word independently, basically. So when we have the word legal, okay, it is represented as just that one-dimensional vector. Well, it's not one. So the vector that we represented in is the dimension of the dimensionality is how many words you have in your vocabulary. But then the word legal has just one non-zero value in that vector. Okay, and that dimension is that dimension legal. Okay, for all the other words, it has the value 0. Even when you have a dimension like lawsuit, for example, which should be very, very similar to the word legal. Okay, so there's no notion of similarity of words when we represent the words in this basic topic model. So, in the LDA model, so a document is represented by a bunch of topics, and a topic is represented by a bunch of words and their probabilities. And word is just represented by itself, nothing else. But when we think about words, okay, we had this. I think this is a Nature paper that we like, and this Nature paper was talking about clustering words into these communities, but not by words themselves, but by the links between the words. Okay, so you can see, for example, Newton appears here. Newton, when it co-occurs with relativity, that's a science topic. Okay, that link between relativity and Newton is a science, or maybe a physics. I think it's like a physics topic. Okay, or maybe this. Okay, so this pink is maybe this Newtonian physics topic, represented by Newton and Apple, and also Newton and gravity. You can see, there's a chemistry topic here represented by this light blue links. So chemistry and velocity, chemistry and test tube. And then the biology topic here represented by these magenta links, biology, biologists, and so on. So that was our motivation. So we said, why don't we represent words not just by themselves, each word independently, but by the links between pairs of words, okay? So then the overview of our model is that when we have an article, we're going to represent the words in each article as a network. Okay, we're going to look at the links between the words, and I'll tell you how we make the links in a little bit. And then when we have the links, just like the Nature article did, we're going to cluster the words into their topics, but not the words themselves, but the links between the words, okay, as different topics. So you can say that in this article, there are 3 topics, sort of like what we had before with the regular topic model, but rather than putting individual words into each topic, we're putting this relationship between pairs of words into these topics. Okay, so the way we construct the graph. So first the first step is to construct the graph of each document. And so when we're looking at the word fraud here, we're going to look at the small window of neighboring words, okay? And I said 7, but the illustration shows a little bit more than 7. So that's the narrow window in which we look at words. So being accused of securities, all of those are my potential words that I'm going to make links to from this word fraud. Okay, so fraud is a node in my graph, and I'm going to have other nodes in my graph that are other words, and whether or not I make the link is first determined by whether those 2 links appear in this small window together, and then secondly, whether the similarity between those 2 words is above certain threshold. Okay, and this part of word similarity actually comes from such that these words in bold become related, or they get linked to the word fraud. Okay, when we make the graph for this document. Okay, and so we come in the end we come up with these 5 words that are now related and are linked with the word fraud. Okay, accused, securities, major, investor, and sued. And here already you can kind of see when we try to cluster the topics, fraud and accused is going to, well, in the end it's going to go into the legal topic area, whereas something like fraud and investor or fraud and securities, we hope will go into the financial topic, or the financial perspective of fraud. Okay. Oh, okay. So this is not mathematical, but this is the generative view of this model. So I'm sorry for putting this in, but this is the generative view of each document under this DCTM. So what I was kind of trying to tell you before with the basic LDA model is very similar to this, and I'll explain the generative process, where the number 1 for each topic K, we draw the word distributions. That's the same for both models, but this part is somewhat different. So for each document, instead of just generating, okay, so this step does not occur in the regular LDA model. For each document, it draws a topic distribution, and then for each word, it draws a word from that topic. So that's the version I was trying to tell you. You know, I'm going to write my first word. It's going to be about biology. So I look in my biology topic and draw the word medical. Okay, so that was the generative process. But instead of doing that, I'm going to first generate some kind of a graph. Okay, and with it using this graph, I'm going to look at each link. Okay, and generate a pair of words based on that link. Okay, so probably not a good explanation, but that's that kind of illustrates the difference between a regular basic topping model, and this DCTM that I was trying to illustrate. And I think I forgot I forgot one slide where these similarity numbers come from. But some of you may know. It's called word embedding. So this neural topping model or neural language model where we represent each word not just by itself. So when we have the word legal, we want to capture the fact that the word legal is very closely related to the word lawsuit. And how do we do that? So the deep learning community have come up with these neural embedding models of words such that in this very high dimensional space, we're going to represent each word, such as legal, such that it appears very close to the word lawsuit. If you have the word medical, it's going to appear very closely to the word doctor. And how do you do that? You do that by looking at words that appear next to each other in a bunch of documents. Okay, so the details are not very important, but the difference between a regular LDA model where each word is just represented by itself, there's no relationship between words at all. In this word-to-vec model, word embedding model, we have this notion, or we can compute the similarity between the word investor and fraud, major and fraud, and sued and fraud. Okay, and this is the similarity number that you get, and you can see how the words in bold have a high similarity, whereas the words that are not in bold have low similarity value with the word fraud. Okay, so basically what we've done is we've combined this document level context that the topping model captures, and then this word level local context, neighboring word level local context that's captured by word2vec, and then we're combining them into this larger topic variant of the basic topic model called the DCTM. Okay, so I feel I haven't explained the model fully quite yet, but I will move on to the experimental results part. Maybe this will give you a better idea of what the model actually does and how it does it better than a basic topping model. So in a basic topping model, you can't have things like this. So you can't represent a document by a graph of words. But here we are representing a document with a graph where the links between two words mean that they occur in this small local window together. So they are somewhere in the document close to one another, and that their word similarity is quite high. And then once we have the links, we cluster the links such that we have a blue topic, we have a red topic, and we have some green topics here, but very little. So you can see, okay, so we did this with a bunch of, I think something like 10,000 academic papers, and this is actually in a bunch of papers in computer science. And this one paper called Hierarchical Multi-Agent Reinforcement Learning. So you can see that this paper is about two major topics. One is about reinforcement learning, okay, and the other is about multi-agent learning, multi-agent AI, kind of a topic. And if you look at words like learning, for example, it occurs in this machine learning topic, which is this, or reinforcement learning topic, which is this blue topic, and then and it also occurs in the red topic, which is the multi-agent topic. Okay, and that depends on whether this word learning is a reinforcement learning word or an multi-agent word, depends on which word that it occurs closely to. So if your document has, let's say, 10 occurrences of the word learning, it's going to appear some of the time in the reinforcement learning context and some of the time in the multi-agent learning context, and that depends on the neighboring words of that occurrence of the word. Okay, so you can see when it occurs next to agent, it's in the multi-agent topic. And joint is another word, and we call those words topic bridge words, or sometimes, for now we'll say they're bridge words that bridge the two topics together. Okay, so here's another example of topic visualization, and this paper is about databases, actually. So it's about this object-oriented databases and how you optimize certain things within that within that system. And it has several topics, one of which is this blue topic, which is about the language, or the database language, okay, the semantics of the database language, and then the red topic, which is about how to optimize. Okay, so again, you can have words that bridge. So languages, for example, and other words like meaning, for example, meaning occurs in the language topic as well as the optimization topic, depending on the context, depending on which other words that it occurs next to. So the CS corpus is a little not very interesting. So we also did experiments with news data. So in computer science, in machine learning in general, when we develop a new model, we have to have at least 2, sometimes 3 data sets to try out our method, to show the generalization of our method. So with this news data, we were trying to show how we are able to find topics, for one thing. Okay, so we found the technology topic, we found tax, city, environment, government, and transportation, and we have these words that act as bridges between these two topics. So you can see how the tax topic has these really top words that are really about taxes, like tax, income, pay, and so on. But then there are these bridging words like cost, provide, housing, fee, that are in between this tax topic and the city topic, okay? And the same thing with other bridging words as well, which it seems kind of silly and very obvious, but this is pretty hard to do, or it's actually impossible to do with the regular LDA model, because in the regular LDA model, it's just like words belong to different topics, and there's no notion of words that bridge the two topics together. Okay, so that, I think, was kind of cool. And then, there's this evaluation metric called topic coherence. So you may be wondering, so when we come up with these topics, and I haven't told you how to evaluate the results of the model, okay, which is very important in the machine learning community. If you can't evaluate, you can't publish. Evaluating meaning, I have come up with this new model, DCTM. It performs better than the LDA, okay? We have to show that quantitatively. And there are various metrics to quantify whether a set of topics is better than another set of topics. And there's no right answer. So can you imagine if you have 1 million articles in the New York Times and you have to come up with 300 topics, and you somehow do come up with 300 topics, but then how do you say that those 300 topics are the best topics that you can get out of your million articles, or even if it's like 10,000 articles, right? There's no good way of saying that these topics, this set of topics is better than this other set of topics. So people have been experimenting with different evaluation metrics. One evaluation metric that has been kind of trending, or that has been used many times, is called topic coherence. So it basically takes another external corpus. So it's kind of circular, but it takes another external corpus, like Wikipedia, for example. Wikipedia is a good, widely used source for computing topic coherence, and it counts how many times these pairs of words occur together in a single document. So the assumption there is each Wikipedia article represents a single topic, which is a simplifying assumption. But then if the words occur together in that one article together, then they are coherent. Okay, so that's a coherent pair. And for the topics that you've extracted from either your LDA or our DCTM, we look at the top scoring, the top probability words, and we measure how many times they occur together in Wikipedia, and that tells you that we've probably come up with a coherent set of topics. So it is kind of circular, but that's one way to evaluate the results of topic models. So to make this long-winded story short, our model called DCTM performs actually quite a lot better than the LDA model. This is actually a pretty good improvement considering other variants of the LDA which have also shown improvements over the LDA for topic coherence, but probably not as much as our model. Okay, so that was one metric. So that means by incorporating the links, and also by incorporating this fine-grained representation of each word in this high dimensional space using word2vec, we're able to better capture the topical patterns in our data. Okay, so that's what that comes down to. This is an interesting task. So in a lot of these text mining research, it's good to show these sort of semantic language tasks that are sometimes a little tedious and maybe nonsensical, but we do it anyway. So we have this task called missing word prediction. So we just randomly remove a word, and then the algorithm has to decide or predict what word goes in there. So we're going to remove this word. Does anyone remember what that word was? If you don't remember, what do you think it is? Do you think it's fraud? No, right? It's not going to be fraud. Is it going to be Alice? No, so that's the task, right? So given this local context and this document context, we're going to the model's going to try to predict which word should go in there, which is a very difficult task. Let's see, what was it before? Oh, okay, it's reinforcement. Who would have guessed? Okay, so there are a bunch of words that you can guess, and usually you can't guess the top one, right? So then we guess, the algorithms guess a bunch of words that could go in there, and then, my number one choice is this, my number two choice is that, and so on. And then we do the inverse of that and compute the average inverse rank of the actual word. Okay, so it was reinforcement learning, and let's say LDA picked that as the 95th choice, whereas DCTM picked that as the 35th word. Okay, so in that case, DCTM is a better model because it had a higher rank for that word. So basically, you can say word2vec actually does not do very well because it doesn't. Word2vec is just looking at similarities of words, so it's actually just not. This is not a fair comparison. It's not. The purpose of this is not to do that kind of task. You could do it with LDA. You can model each topic of each word and then try to guess the topic of that word and then generate some words based on the word distribution, multinomial distribution of that topic. It does pretty well. I mean, it's really hard to say whether this is good or not, but the point is that our model does it better. So you can kind of see this is kind of an obvious result. Because we're using a lot more complex model, we're looking at both local context and document context. So it's actually bound to do better. If it doesn't, then there's no point of doing this, more complex modeling. So, and then the third experiment that we did was to see how having this local context makes our model better or worse, or actually better, how it improves because of the local context. So to see that, we randomly corrupted the word order of the document. So you can see like all the words are the same, but they occur in different places. Okay, so it's sort of a jumbled up version of the same document. And so what we did is we did document classification. So what that means is if you have the New York Times, 10,000 articles, and each document, each article belongs to a section, let's say sports section, politics section, economics section, and we try to, without having that as our labels, we try to predict what that category was based on the topical distribution of each article. And because the topical distribution is the output of both LDA and the DCTM model. Okay, so this is the result. So document classification, because we're trying to predict the category, the higher is the better, right? So if it's 1.0, then that means you got everything correct. LDA. And these are the two clustering methods that we used. It doesn't matter too much. K nearest neighbor and naive Bayes. It performs around, I don't know, 67, 68%, which is okay, but not that great. We did better, more than 70%. But if you, with the corrupted version of DCTM, this actually does worse, which, for us is good news because we are actually, the model is actually capturing and using the local context information wisely to improve upon the corrupted version, which kind of improves upon LDA as well. So this is kind of curious why it does better even with the corrupted version. It actually is because of the word similarity captured by word2vec, right? So if you just have word2vec and LDA put together without having the links that capture the neighbor local context, then this is probably what you get. So from LDA, which is the basic model, if you use word2vec, this is the improvement that you get. And by capturing the local context using the links, this is what you would get in the end. Okay. So I think that's the end of the technical part of my talk. So in summary, topic modeling is a very, very widely used text modeling, text mining method, but it has a bunch of limitations, and we try to address two intrinsic limitations. That firstly, that the local context is not captured by the basic topic model, and secondly, that words are represented as if they are independent from one another. And so this independent assumption we try to improve by using word2vec similarity metric, and then and the word2vec model that we do use to capture similarity, it represents each word in a high dimensional space, and it preserves the contextual similarity of the words, but Word2Vec has the limitation that it's actually not modeling. It's not a model for documents. Okay, so it's just a simple model for words and their similarity. So by sort of just simply combining the advantages of Word2Vec and LDA with this notion of links to capture the local context, we have made this dual context topping model, which improves upon LDA and Word2Vec in quantitative as well as qualitative results. Okay, so to step outside of this DCTM for a little bit and tell you about some other research that we do so that we can talk about collaborative research opportunities. So we've been doing this topping modeling for quite a long time. In terms of the statistical properties, the model that I've explained today is a parametric Bayesian model. You may be, because I'm in a math department and I know that Professor Yeonseung Jung works on Bayesian nonparametrics, there's a set of topping models that are based on the Bayesian nonparametrics part of the statistics world. So that's it's a whole class, a whole other class of models that we look at. We apply the topping models to documents as well as social media data, which means that we do some kind of computational social science research as well. We've been looking at automotive driving data. Actually, this deviates a lot from our text mining, but the text mining methods can apply to a bunch of other types of data, and automobile driving data is a class of data where you have a bunch of high-dimensional time series data. So we're applying deep learning as well as other machine learning algorithms there too to understand driver behavior. Okay, we've only done this for a year, but it's really exciting work. So, for example, you can predict whether somebody is risk tolerant or risk seeking based on their time series data of driving, where time series driving is like how fast you put on the brakes, how much you do the steering, and so on. So it's a bunch of high dimensional data and at 10 hertz. So you can imagine if you're driving for 30 minutes, that's a lot of data points. Coming from a bunch of different sensors from your car. And if you apply some machine learning data, you can learn all kinds of really interesting stuff about you. All right. Lastly, this is really different too. We're trying to improve computer science education. Again, the underlying methodology here is machine learning too. We get data from students while they're typing on their programming assignments. And we look at their typing behavior. We look at their the variables that they tend to use. We look at the questions they ask, all kinds of things, and we're trying to determine who is on their way to successfully solve this problem versus somebody else who is making all kinds of changes to their code but is struggling and not going to get to the solution that we're expecting the student will get. So these are sort of three big topics that we're working on. If you are interested in any of the research topics, and as you can imagine, even though I didn't talk about it, it's all driven by machine learning, which is driven by statistics. So I am looking for your input and your opinions and your collaboration. Thank you.